Okay, so good morning, good afternoon, everybody. My name is Ivan Castillo. I'm part of Dow Chemical that now the name is Dow Inc. after some split with multiple companies. So before starting, I would like to thank Martina and the organizers of the forum for this invitation. I'm really happy to have the opportunity to share some of the experiences in big data analytics that we are having in Dow Chemical. When I saw the theme of this forum, I was really excited about the plan of the future. And one thing that I have learned in these years in which I've been working at Dow, like around 10 years, is that so Dow has been in a journey on digitalization, and we found that big data analytics is a really important player. So when I was looking at this theme of the plan of the future, and uncertain that actually big data analytics is even more important. So in one of the points of my talk today is going to be about what features are required for the plan of the future. So what kind of big data analytics methods we'll need in order to make it to serve best for these plans that are coming. So the other authors are Leo, Ricardo, and Mark. Those are part of my organization. I'm part of the Chemometrics and AI group. So this is it's a group that we are focused on analytics and we apply it across all the organization. I was really happy with the presentation of Mercy as he claims himself as a data artist. This is the first data artist that I meet, but it's very nice. I tried to, you will see some of the art in the focus on the chemical industry today. And you will see that it's a very nice art, even though some of the people in my company don't believe that it's art. Um, okay, so first, before starting, for those that are not that familiar with analytics, so why we're doing this? So the final goal and the final ultimate objective is to drive decision making. So we apply analytics for that purpose. So there are multiple stages when in order to reach this decision making. You start with a huge amount of large data. This data cannot be only numerical. It can be also images. It could be text. It could be multiple types of data. And then typically, and for those that are data sciences practitioners or your life you spend in data sciences, you will know that there are mainly two stages in order to perform analytics. The first one is a data management stage, which is actually one of the most time-consuming stages in the entire process. So some of the examples of those tasks that you need to do is data acquisition and recording, extraction and cleaning, integration and aggregation. So these steps are really time consuming, specifically if you have 10 plants around the world and each of the plants have different type of variables and you need to mask them, and it's a lot of work, like I would say 80% of the entire process. Then you go to the next stage, which is the analytics. So in the analytics, we try to find different questions, and depending on the questions that you want to ask, you might need to use different approaches. So today in my presentation, I'm going to show some of the approaches. I'm going to be more specific what I mean with these questions. I'm pretty sure you heard about these descriptive analytics, diagnostic analytics, prescriptive and predictive. So each of them have a purpose. Like the basic one is descriptive analytics, in which you are able to identify what happened. Then you go to the next one, which is diagnostics, which you need start asking for the root cause. And then you go to prescriptive, so you are able to take an action. And finally, you go to predictive, so you are start to anticipating in the future. So we're going to talk about some of them during my talk. But if you are interested in reading a little bit how to start this journey, how to start with a big data culture, so I would recommend this paper. This is a paper written by some colleagues in at Dow. As I mentioned, we started this journey around 2016, and it's been a very, very fun in general. So for you to give you an idea of the type of challenges we face when we are working with data, we can summarize them in based on the 4 Bs that are used in the concept of big data analytics. Not sure if you guys heard about it, but typically we have a lot of volume of data in a plant. Usually we have 10,000 tags or variables, and we have data for around 10 years in second or minute data. So it's a significant volume of data. So you cannot get that data in your computer. It gets just trash. But also we have a lot of variety of data. So we have, as I mentioned before, we have a lot of images, we have text, we have different type of processes that brings different type of data. I'm gonna mention a little bit about that. For instance, batch type processes, continuous processes. And then also we have some data that we have issues in veracity. Or it has a lot of uncertainty or have issues in quality. So these processes, I mean, sometimes you can have a lot of data and it's not useful at all. So that's also important to recognize. And finally, velocity, which is more real time. You need to have some conclusions in seconds in order to maintain your process operating at maximum. So these are the typical problems that we work. I'm going to show some of them along this presentation. And then when I was invited to this presentation, the first thing that came to my mind is, wow, how big data analytics can serve the plant of the future. And so I here listed some of the features that are, or the capabilities that are, based on our experience, we believe it must be in that space. Like this is kind of like the big data of the future. So I want to mention here that these features are only applied to manufacturing process data. So like for instance, in Dow, it's a huge corporation, and analytics is applied not only in manufacturing or in the chemical plants, they are also applied, for instance, in the customer interactions. And for instance, in business, that is called business analytics. So there are multiple branches that are not covered here. Here, I only focus on the process in the chemical, in the unit operation, and these are the attributes that must have a big data in order to serve the plan of the future. So those are I'm going to mention today. One of them is accelerating process for troubleshooting. So this is a really important thing that we need to find certain techniques that are able to do that. The second one is improving measurement accuracy. Third one is optimizing plant operations. Fourth one is analytics plus first principle models together. So this is a really interesting one because we have a lot of models, fundamental models, and we need to be able to combine it with analytics. Another point interesting is, okay, how we're going to maintain the models online. So we have models that have 1 million parameters, how they are going to behave after 6 months and when they are deployed in the plant. The other point is bringing information from non-traditional data. So this is something that really is starting to be more and more frequent. Specifically, an example is we use the logbook of the operators in order to try to predict unplanned events. So batch data analytics capabilities, I'm gonna mention this in the slides later, what that means, but it requires some capabilities in that sense. And overall, all of these that I mentioned is with the objective of have self-service analytics. So meaning, I'm not sure if you guys heard about this term, but the idea is that you, as an operator or as a plant engineer, you are able to have certain tools and try to apply analytics in order to ask your questions. So this is where we're going. So far, all the things that you see here are performed by data scientists, but we want to get that it's going to be applied to everybody. We want to reach that point. Okay, so I'm going to start mentioning some of these capabilities. I have here 3 case studies. I'm going to go quite quickly. So this one, the first one is with the purpose of accelerating process troubleshooting. So what we use, and this is actually related with the presentation of Marcin in the previous one, is related with visualizing high dimensional data. So, and this is a little example. If you look at this picture in here, it's very simple. It's not like the Marcin's pictures, all these. This is, imagine that you have a cup. Um, Please forget this DAO logo. And then you have this picture, this image, or this cup that is actually 3D, and you want somehow to represent, to get the most information of this cup, but try to do it in a very simple way. So one way that you can do is you can take the picture, you can take this, like take the 3-dimensional object, and then you have multiple colors and things, and do a very fancy analysis. But also one thing that you can do is you can reduce this object from 3D to 2D. So if you look at the shadow, so this shadow is going to give me also information about the object of the cup in this case. So this is the idea about visualization. This is an indirect method, and the idea is to use dimensionality reduction. So we try to imagine that you have 1,000 variables, and we try to reduce it in a space that is more easy to visualize. And in here is where we see a lot of art. It's beautiful, and we find certain patterns in the embeddings that are helping us to troubleshoot very quickly the data. So here you can see some advantages when you apply dimensionality reductions. First, increases interpretability. This is what we are looking for. You find clusters, outliers in your data. Second, decreases the risk of overfitting and noise, eliminates irrelevant and redundant features, and decreases computational time. So this is one of the techniques that we use, and definitely are really helpful to accelerate process. Here you can see the techniques. I'm not gonna go in detail about these techniques, but typically you can divide it in 3 groups: in unsupervised, supervised, and reformer learning. In the unsupervised technique, you find these methods: PCA, principal component analysis. Not sure if you guys have used it in the past. TSNE, UMAP, these are more new and recent, and have demonstrated to be very effective, and autoencoders, which are based on neural networks. And then you have also supervised, which the difference between this one and this one is in unsupervised, you just take your data and naturally you try to find patterns of the data. In the supervised, you have already some output, and you are sort of, you have some idea of the classes or the problem, so you can put some labels on your data and also use it in that way. So if you want to see further details about visualization, I would recommend this paper. These are showing some cases on industrial case studies in chemical engineering, and it shows very good results in terms of these 2 techniques, TSNE and UMAP. We did a very extensive comparison of all the methods available. So I'm going to show the first case study. It's a very typical case. This is a reactive approach. The objective here is understand what happened before an unplanned event is occurring in a plant. So on the bottom plot here, let me, I'm going to put my pointer. So in the bottom plot, this is a typical key indicator for the plant when they are kind of like they are monitoring, and when the operator or the engineer, they have their own levels, so they know when, depending on the values of this indicator, they know when the plant is normal. Then they start getting a little bit worried. So you see this indicator start increasing a little bit, and finally you go to the final stage, in which it's start getting a little bit very high in your indicator, and until you reach the point that definitely the plant needs to be shut down. So this is a really typical example. Usually in the plants, engineers have their own indicators, but what is difficult is to identify the reason. What are the reasons behind this? Why it wouldn't be able to stay here in this stage 2 for longer before they shut down? So in this particular example, we have like around 200 variables. And then one of the techniques that we use at first is principal component analysis. So you can see the colors correspond actually to the labels that the engineer was sort of putting at the beginning. So, and definitely you can see here, this is you look all the 150 variables summarized in this plot, and you see first that the engineer is right. So you see that naturally you can see in the colors the progression that he's mentioning the stages. So this is kind of like the art that we have. This is a very nice picture. I have actually a lot of pictures in my house in terms of these embeddings, but it's really an art. I hope you guys also see it as well. But by using another techniques, let me put here. So in particular, UMAP and TSNE, we start finding more details on the data. So notice, for instance, in this cluster green, which is corresponding to the last part before the shutdown, so we start finding more details. So it's even more, it provides you, this thing is a little bit more information than even the basic principal component analysis. And then you are able also to drill down and go back to your data. And then these two clusters that you see in the green stage, in the stage number 2, you can see that there are something happening in some of the variables. And this is the information that we provide to the engineers in order to, in a future event, try to avoid those. This is a very nice case study, very typical, and we use a visualization technique. So this is important, and following Marcin's presentation, we found visualization in one of the most important aspects in big data in order to accelerate process troubleshooting. Okay, I'm gonna move to the second case study. In this, is related with bringing information from non-traditional data. So we have in one of our businesses, we produce pellets, these are plastic pellets. And the idea is we want always have a very good pellets and identify those before we send to customers. This is an example of a bad pellet, like looks like a mushroom, or these ones that have a little bit of tails, and besides of having like a very weird shape. But in this one, what we did, the current system has an image analyzer, which is the name is particle shape and size distribution, PSSD. And this is the vendor solution. And what they do is they extract features from the images, and then they apply some sort of algorithm that is not is confidential, and they get an accuracy of 80%. So we did two things in this case. First, we took the same features that the vendor develops or extracts about the morphology of these pellets, and then we start applying machine learning approaches, in this particular case, random forest. And we already, with using the features, we increase accuracy. And this information is impose a lot of pressure to the vendors, because we are telling them, listen, we have a solution that is better. So they start changing their methods and improving. So, but we went a little bit further. So one of the techniques is extracting features of the images, but also instead of doing that, you can just basically use the image directly. And when you use the image directly, you can apply other type of techniques, which is deep learning. And when we apply deep learning, we even increase further the accuracy. So these are interesting techniques that we are starting to use. So we have demonstrated with multiple case studies that deep learning is really effective in the case of for using it for image classification. So in this case, you put any of these images, and the deep learning model is going to tell you if it's good or bad, or it has tails. So one of the inconveniences is that we needed a lot of images in order to develop this model. So we have to invite all of our experts of the business, bring cookies. In that time, we weren't in the COVID-19 issue, so we bring cookies, coffee, and we ask them to label each of the images. And they help us to label around 6,000 images in order to develop this model. So there are some disadvantages, definitely. But we found that even with only these 6,000, we were able to increase accuracy. So if you want more details, also there is a very interesting paper that mentioned this case study. Okay, I'm moving to the other next case study. I think I'm getting out of time now. This is related with improving measurement accuracy. Uh, we use sensor fusion, which the idea is you have multiple sensors and you it's capable to mix it in order to increase accuracy. So I'm going to skip a little bit this. I think I'm getting a little bit of time. But basically, the idea is you have multiple sensors and you are able to combine them in order to get a better estimation of your variable. In this case, it was an impurity. And then when mixing different sensors with different rates, you are capable of having the, uh, the best prediction. And this is what we call fusion. So I don't want to get too much. I think I'm getting out of time now. I wanted to talk a little bit about plan optimization, but I'm going to skip these slides and I'm going to go to the challenges. So, so basically, one thing that we see and thinking about the plan of the future is that so we need to find the right fit for these new analytics approaches. In particular, deep learning, we found that it's very useful in order to be using in images. So that's one of the important challenges. So, but in order to do that, we need to create a lot of case studies. We provide a lot of data to universities and research labs in order to do that. And this will help us to speed up adoption. So we have issues in the plans for our engineers to adopt models that are black box models. So we need to incorporate hybrid approaches, meaning mixing between models um, and data-driven approaches in order to improve interpretability. So that's something that is a huge challenge currently. And the other point is the model maintenance. So once the models are deployed real time, we need to see how we're going to maintain them. And for instance, a deep learning model typically has 1 million parameters. So how we're going to do in order to keep it running. So with that, let me go to the last slide. So I just show in this case only 3 case studies. I wanted to show 4, but unfortunately for time I couldn't make it. So these are some of the capabilities of the plan of the future. So one of them is accelerating process troubleshooting. The other one is improving measurement accuracy. And the other one that I mentioned was bringing non-traditional data. So with this, I finished with my presentation and I will be happy for some questions.